Hey guys, welcome. This is a 5.3 video. So we got some vocab that we want to go ahead and take care of first, and then we can go ahead and jump into some problems. Alright, so the first thing is we got a bunch of vocab, so let's go ahead and talk about it right here. I don't know who that was. So this segment right here, I'm just going to read it to you. It says, if the three lines that you drew intersect at one point, the center of the circle, that was from above, so we don't need to look at that, but it says when, right here, when three or more lines intersect at one point, they're called concurrent. Okay, so that's a definition, make sure you write that down. And the point at which they intersect is the point of concurrency, so you guys can just write that point down. What we're talking about is we're going to be talking about a couple of different scenarios where we're taking perpendicular bisectors today, and we're going to be talking about angle bisectors and where they meet and what happens when that happens. Okay, so our essential understanding is for any triangles, certain sets of lines are always concurrent. Two of these sets of lines are perpendicular bisectors, which we're going to look at, and the bisectors of a triangle, which would be our angle bisectors. Okay, so again, just have to write this. We're not going to actually write that right here. We're going to go ahead and scroll down real quick and take a look at what we are going to write, which is this right here. So this is one of our big keys. It's called the circumcenter. Okay, so we're going to talk about the circumcenter and the incenter today. So the circumcenter is the points of congruency of perpendicular bisectors. Okay, so when we have three perpendicular bisectors, so all three of these are perpendicular bisectors, they're going to actually meet and create the center of a circle that is called circumscribed about the circle. Basically, since the circumcenter is equidistant from the vertices, here are the vertices B, C, A, they're equidistant, that's how we know it's the center of the circle. So we're going to go ahead and take a look at what that would look like. Here's another picture of it up here, but what I'd like you to do is write down the definition for this piece and the definition for this guy. And please draw this picture. This is a great picture right here. Okay? Alright, before we kind of go into the other vocab, we're going to actually take a segue and move into using one of these problems. So let's look at the circumcenter of a triangle and what we can actually do with it. Okay. What are the coordinates of the circumcenter of a triangle with vertices 0, 6, 0, 0, and 4, 0? So we are going back to the coordinate plane, so we're going to want to make sure that we can go ahead and utilize this. So moving my face down over here. Moving forward, let's go ahead and take a look at drawing the picture first by itself. So here we have, kind of still in the way a little bit, here we have our triangle drawn. Okay, so we got our points 0, 6, 0, 4, and 0, 0. So we can go ahead and label those POS, and then continuing on. What we want to do is we want to then, since we're talking about the circumcenter of a triangle, we're going to find the perpendicular bisector. That's where they're going to meet. Okay, so we're going to go ahead and do this easily first by finding the perpendicular bisectors of two of these. Now this is pretty simple for vertical and horizontal lines. So if you take a look at this line right here, I don't know why I keep doing that. This is right here a vertical going up and down, and this is a horizontal. So you can actually find the center of this because it's going to bisect. So half of 6 is going to be 3, and half of 4 is going to be 2. And to be perpendicular, it's going to be pretty easy for us, but we're just going to go ahead and draw a line right in here. That's going to be perpendicular. And then we're going to draw a line right here. That is also perpendicular. So my incenter is going to actually be right here. Or sorry, not incenter, my circumcenter. The circumcenter of the triangle is right here. And that's going to be at 2, 3. Okay, now we didn't have to do the third one because if we have two of this perpendicular bisectors, we're going to actually find it. So the third perpendicular bisector would actually go through here. It'd be a little bit harder to graph on here, but this one we can easily find. So I just showed it to you there. That's all we have to write down for this problem, but I'm just going to kind of let it run its course, and you can see kind of how they do it here. So they first found the midpoint, which we did, and then they did the horizontal to the vertical, and then they moved it on, found the midpoint of the bottom segment, which we did as well, and that went from horizontal, so they draw in the vertical, and right where those two meet is called our circumcenter at 2, 3, and that is where we have it. And does the location of the circumcenter you found make sense? Does this seem like it would make sense? I believe so, yes. If we actually were able to draw a circle around this thing right here, if I can kind of, let's see, ooh, I have a circle tool, don't I? Oh, this is going to be cool. Ooh, ellipse. I wonder if I can make that into a circle. Yes, I can. Let's see. I wonder if I can I move it? No, I can't. Let's try that again. I think I can do it. I think I can. Or you can just skip me trying to do this and go to the next problem. Maybe if I start here and I pull it. No, I gotta start it at a point. That point is, I have no idea how I'm gonna actually make this work. Okay, come on, one more time. Almost. That was almost there. Maybe I should eyeball it. Again, you can move on if you want to. Ooh, really ugly, but it kind of looks like it's hitting almost all the points. That's really ugly. But that's a circumcenter. The shape is circumscribed by it. This would be the center of the circle then, using our perpendicular bisectors. Okay? So let's go ahead and deal with this in another way, is by taking a look at why do we even care about the circumcenter, and that's why we're going to go to this next problem. And I just want to show you this problem real quick. We don't have to actually write this down, so you don't have to write it down. But basically what's going to happen is they want to know where can we put a new fire station and it would be equidistant to all these 3 places, the high school, the elementary school, and middle school. What we'd want to use is the circumcenter. So again, we're not going to do it, but here they go. They kind of pull it out. Like, here's a triangle, perpendicular bisector. So that's where they'd want to locate it. Now, we know it's going to be equidistant because, holy moly, that's a great looking circle. If this was truly the center of the circle, these would be all radii, and they'd be congruent. So again, you didn't have to write that problem down, but I thought it was so cool to look at. So let's continue on back to our vocabulary. And by the way, and I think this is kind of cool too, and I want you to go ahead and write this down as well. The circumcenter of a triangle can be in many locations. So this right here, please write. Basically, what we can have is the circumcenter can be inside if it's an acute triangle. So the circumcenter will be in here. So if I drew the circle around there, look at that, that makes sense. It can be actually on the triangle if it's a right triangle. So something like that. And if it's an obtuse triangle, it's actually going to be outside the triangle. And that's nowhere near what it's going to look like. But yeah, something probably like that. So we're going to get the center of the circle outside. So those are different ways that we can kind of see it and what it might look like. So I thought that was kind of interesting. Let's go ahead to our last thing, and this is going to be called the incenter. Okay, so here's the incenter of a triangle. So we're going to go ahead and write this down. You don't need to write this down. But the incenter is the points of congruency of angle bisectors. So we have all of our angle bisectors. And it's called the incenter. For any triangle, the incenter is always inside the triangle. So it's always going to be inside the triangle. Again, you're writing this down and drawing this picture. And so we have X, Y, Z. These points are equidistant from P, and incenter means we can inscribe a circle inside of it. Okay, so let's go ahead and take a look at an example of this. Again, you don't have to draw this, but please write down that vocab. And let's go to our last problem. Our last problem here, okay? Identifying and using the incenter. Okay, so overall, this is what we have. Here's a picture. GE and GF, this is great, but basically all of these are angle bisectors. So CG, GB, and AG, these are all angle bisectors. You can tell because they're bisecting the angle. So this point right here, point G, that is the incenter. for some reason it has a real trouble picking up a dot. Let's see. There we go. Maybe I just gotta do a little circle. So G is the incenter. Because G is the incenter, we actually can find the measures of these other segments, because F, E, D technically are kind of like our inscribed circle. So a circle that would fit inside of here. Again, my picture's not perfect, but this would be the center of that circle. So these are all equidistant. They're like radius, or we call it radii of this circle. So when it says GE, GE, boom, and GF, GF, boom, those are congruent. So all we have to do is set them equal to each other, and we can solve. So here we go. So I'm going to subtract the x over here and add the 7 over there. So we'll go ahead and do that. Add the 7 to this, that gives me 11. Subtract the x over here to give me x equals 11. Now it wants me to find GD, so I'm not going to stop here. I'm going to plug it back in to GD. Well, it doesn't matter. I got to plug it back into actually one of these because I don't know what GD is, but they're all the same, so it doesn't matter. So here we go. GF equals, and we're going to do 11 plus 4. So GF, gluten-free, everybody. Isn't that nice? GF is 15, and GD and GF are congruent, so we can say GD is also equal to 15. Alright guys, I know that video is kind of long, a lot of explaining, and the next video is going to have 2 more of these type of things, but again, just to review, we talked about the incenter and the circumcenter. So both of those 2 key concepts for us, so we'll see you guys later. Hats off to you.